So we're finishing this part this week. Basically, we're adding more description into our model. And there are two things we will consider, and we will do it with example. One, we are improving the model. Now we have the two-axis model for a machine, and we will finish talking today about that. And the second part is how we deal with multiple machines, and that's very realistic for a power grid. So last time we were talking about the part transformation and the meaning of that, and we used the rotating magnetic field to understand what is the meaning of these D and Q components that we're getting for all set of three-phase components. It can be current, flux, voltages. And we were here. That's the model that we get physically from the system, and we were talking about the behavior of the dynamic associated to this differential equation, the one in blue. By looking at the physical description of this, we can observe that the dynamics for these are very fast in comparison, of course, to the dynamics related to the motion, but also to the dynamics of the flux related to the field winding and the 1Q damper. So the typical procedure we have here is that we're going to assume that the dynamics of those state variables in blue related to this equation in blue are going to can change instantaneously. So the energy involved for these 5 equations we have there is very small in comparison with the others, and therefore the variables can change instantaneously.
This question. So it makes sense that the energies associated with the flux linkage is pretty small, so we assume it changes instantaneously. But why do some flux linkages we consider fast and some flux linkages we consider slow? Like, for example,
it's related with the physical characteristic of these dampers and where they are designed for. So in the machine, you're going to have a very fast response. In all times, we call this the subtransient response. And that happened just a few cycles after you have a big disturbance, like a short circuit. So it will last very short, but can take into account very large spike in the currents or all the variables in general, but it will die very quickly. And that has to do with the design of this damper. What is the section of these conductors and the number of turns, but the other is designed with different characteristics. So they can have an action that prolong longer in time. So they provide some damping over more cycles, not just the first 3. So it's because of that characteristic that we will see that some of this equation related to some of the damper will die quickly, but other will remain there. For this one in the stator, that by intuition, we will realize that that's not very different to the flux linkages in a transmission line. They're actually in series in the model that we have. So that's something that we would expect for this. But for this one, it's just a physical design. And then when we have this assumption that they can change instantaneously, we did that for the grid, and that was the final model, an algebraic representation. If you have changes in this current, and we consider this current injection, for example, some of them can change instantaneously because of a short circuit, then the voltage will change instantaneously based on that relationship. So now we will do the same for this equation. Basically, we will obtain algebraic equation that need to be included instead of differential equation. So that's, when we do that, that's the two-axis model. Why we call it the two-axis model? Basically because we will have one equation for each axis. describing the dynamic behavior on each axis, the V and Q axis. And these are the two equations you can see right here. There is a lot of algebraic manipulation because we are moving from these 5 equations here plus equation of flux linkages in the machine. If we combine all of them, we can come up to these 2 equations that can be added to our model. We are not going to study all the details of this derivation. As I mentioned before, this is just a sketch. Going through the detail will take us way more time than this, and we cannot do that in this course. So I am presenting to you the model. This is the model. We have the 2 equations for the motion of the machine and 2 equations related to the dynamic behavior of the flux linkages in the 1Q damper in the field winding in the machine. And that's it. These 2 equations, you know, these are related to the terminal voltage and the terminal current in the stator. So typically, we don't do this for the grid. What is the representation we have for the grid in terms of variables? We did it before. Vector of current injection equal to Y bus multiplied by the vector of bus voltages. What kind of equation do we have there? Has 2 characteristics. One, they are in a steady state. Second characteristic, because they are in a steady state, we use phasor analysis, right? We use phasor for voltage and current, right? Does this look like phasor to you? No. But we have 2 sets of equations. So what is the next step here? How we connect these D and Q components with a phasor? And again, that requires some revision of the transformation we have to find some relationship, but I am providing you the answer right here. If these are related to the terminal voltage, how you convert these into a phasor? By doing this. We will take dq minus jvv, all of these multiplied by the exponential of j delta. And when you do that, this in that form is exactly equal to the phasor at the terminal of the machine with a proper magnitude and an angle. Okay? So that's the connection. So how we can describe this better now that we have a definition for phasor? Basically, what we have to do is just to do some algebraic manipulation. For example, you can isolate for BV and BQ here and use that in this form, and we can come up with a phasor equation. If we do that, then the model, before we have this 4 differential equation and 2 algebraic equation, well, those 2 algebraic equations now can be presented using a circuit, using phasors. So from here, you have Kirchhoff voltage law, you have the internal voltage plus the voltage drop in these parameters must be equal, the current leave the machine. So the terminal voltage plus the voltage drop must be equal to the internal voltage in the machine. That is a single complex equation. If you separate the real and imaginary part, then you should get the 2 equations we had before. Yeah. So that finally is the model. Do we like this? Yes, because these algebraic equations are expressed in terms of a circuit that we can connect to the rest of the circuit for the grid. So we can put them together. Yeah. So that's the model. Any questions so far? Because we're going to use this and we're going to expand this and put more machine. Are we okay with this? Now, how we're going to make the connection to the grid? Well, from a circuit point of view, this is going to be connected to lines, transformers, other machines, and we need to include that in our model. Final step, where, as you can see, this is not very straightforward as the classical model. But another thing we need to do, and this is the final part before we start working with an example, is how we're going to determine the equilibrium point. Okay, so this machine is going to be connected to the grid. So what we're going to do at this point of this course, we're going to still work with a system that has an infinite bus, okay? Because that will simplify our analysis. Let's assume we have a slack bus in the system. With that slack bus, then we're going to, for each machine that we have, we're going to assume that because we don't have any AVR, automatic voltage controller, and also we don't have any governor, we're going to assume that we know at the terminal of the generator how much is the voltage and how much is the active power being injected. You did that in 421 in the classical power flow problem. So basically, each generator now is represented as a PV bus. So what is the step to find the equilibrium point? For each generator, we define a PV bus and we solve for voltages in the system. When you solve for voltages in the system, you also know how much is the injected current at each bus. After you solve the power flow, you have that information. So when you solve the power flow in the grid, if you go to one machine in particular, you will know how much is the voltage here and the current leaving here. So it would be straightforward for us. We say, well, if we know the voltage here and the current, all that I have to do is to analyze this circuit and solve for the unknowns. What are the unknowns in the variable? First of all, we need to determine IQ and IV, because we need IQ at least, because that will define what is the internal voltage we have here. Here you have IQ. Okay, so you have IV and IQ, we need that. But also you can see here we need EV and EQ. You have 4 unknowns, but you have a 5th unknown, delta. With this circuit alone, how many equations do you have? We know we need 5 because we have 5 unknowns, but how many equations can you get? You know the voltage and you know the current. Just making, if this is known, you have one equation here, real and imaginary. So you have 2 equations actually that can somehow help you to determine the unknowns. The other equation will come from this Kirchhoff voltage law in this loop. You have 2 complex equations. How many equations? 4. How many unknown? 5. Can you solve this? No. So we need some further equation to solve this. But the thing is, what we can do, because we're finding the equilibrium point, we can assume that the system is at the equilibrium point, so all the derivative of the state variables need to be equal to 0. So we have a bunch of equations that we need to use somehow to find the equilibrium point. But if we use this derivative and we set them to 0, we can find the alternative relationship that can help us to solve the problem. The thing is, this has been done in the past. By enforcing the derivative to be equal to 0, we can work with this circuit and transform it and obtain a circuit that can be used just for the purpose of obtaining the equilibrium point. So this circuit is in general, not when the system is in a steady state, but if we enforce a steady state condition together with the circuit, we can obtain a special circuit, which is this one, that can help us to obtain the equilibrium point. So in this case, again, we will know voltage and current that come from the power flow equation. We know these 2 variables. But here, you can apply an equation here, and you can obtain these variables, IV and IQ, if we know delta. The main difference of this circuit is that this component here corresponds to the magnitude of the internal voltage. And the angle along here is the angle delta. So if you know the voltage, you know the current, what we can do, we can obtain with this voltage and current, we can obtain the voltage at this point. Let's call that voltage E. We obtain that voltage. And the angle of that voltage must be the angle delta. So this circuit is nice for that reason, because all that it will take for us is to determine this internal voltage, get the angle, and that's how we can initialize the angle delta for the equilibrium point. When you have the angle delta for the equilibrium point, this is known. This is known. Then you can solve for IV and IQ, getting the real and the imaginary part. The equations are right here. So if you have this equation, we can multiply by exponential of negative J delta, and then you get this expression right here. This expression right here. The real part of this need to be equal to EQ, but the imaginary part of this must be equal to negative IV. So that's the expression for AQ, and that's the expression for ID that come from solving this when you know that. After doing that, then we will know IV in this case. And we obtain the phasor for this internal voltage E before. So we know the magnitude of this. But as we know IV, we can solve for EFD in this case. So that would be the third step. From this, from the circuit, we can obtain this internal voltage EFD. And then what we're going to do with all these variables, we're going to go to each one of the differential equations. We're going to set the differential equation to 0 because we're looking for the equilibrium point. And then when we make this 0, we solve for the remaining equation. When we do that here, we obtain an expression for EQ prime, and for here, for ED prime. When we do it for the derivative of delta, basically we get omega equal to 1. And until here, all the equation will be, all the variables will be determined. The last equation is the derivative of the speed. If we make that the derivative equal to 0, what we get is this expression. But all these variables have been determined already. So what we can do just for verification for verification purposes, we can verify that this is actually an equality. And that's the procedure. So what is going to be EFD? I didn't talk about that. These are the two new equations we have for the flux linkages in the field winding and the IQ damper. So this is basically an equivalent of the voltage that we will apply to the field winding. So if you want to increase the voltage at the terminal of the machine, these variables need to go up. That's something that we can control by controlling the DC current in the field winding. Yeah? But when you do that, also you will have some impact on this other component that is related to the Y1Q damper. Okay? So again, with this known, when we make this derivative equal to 0, as you can see here, this is known. This is known. Solve for EQ prime. This 0, you know, IQ, well, solve for EV prime. When we make this 0, then omega is equal to 1. And then until here, all the variables have been determined. And the last one I said, if we make this 0, we don't need to determine anything else, but we have to verify that this is actually an equality. I haven't said anything about this before, but this is related to a torque, related to losses because of friction, and the pronunciation of this is windage. Is that right? Resistant with the wind inside. The rotor is moving inside the stator, and the wind creates some opposition to the motion. So that's related to that. Of course, this is hard to model. So we are going to neglect this term. Okay, so these come to you as a recipe. We cannot go through the details. So please follow this step. These are the steps we need to model dynamically a synchronous generator, and also the process to obtain the equilibrium point. It's not as simple as the classical model, but this will provide more accurate result for a real machine. Because of the circuit, maybe some of you will be involved with this in the future. Because of the circuit, the initialization of this is basically obtaining the voltage, the angle of the voltage that fall behind these parameters, okay? Typically, the resistance is 0. So this procedure is known as finding the angle of the voltage behind the quadrature reactance. And we just remember this so we don't forget. How you determine delta in a steady state at the equilibrium point? Well, we need to find the angle of the voltage behind the quadrature reactance. That's the procedure. Example, and we will work on this today. We did this before, but here we model a generator with the classical model. Now we're going to add this detailed model. So the first complication will be, well, we need to determine the equilibrium point. That's the first step. And then we need to apply the short circuit here that will be clear at 0.1 second. And then we need to see what is the evolution of the system. So what do we need to do here to determine the equilibrium point? As you can see, we have the model of the machine, and we have the grid. That's the behavior of the grid. This is the model of the machine. This is not the quadrature reactance. So this is the dynamic model for the machine from the electrical side. So what we need to do to obtain the equilibrium point is to replace this description by the steady state model. And we will do that now. So the first step is to find the equilibrium point of the system. So we will have here the model of the machine. This is the voltage at the terminal. This is the current in the machine. And because we're trying to find the equilibrium point, the model needs to be the steady state model that consider here the quadrature reactance. And here we will have the internal voltage in a steady state. This system needs to include the reactance of the line, and here we will have the infinite bus that in this case is 1 angle 0. So the first problem here, we need to determine delta. But we know how much is the voltage V1 in a steady state. And we need to know how much is the voltage, the current I1 in a steady state. So how do we find that voltage and current? This is the system. Bus 1, line, bus 2, and this is the infinite bus. Here we have a reactance, and somehow we need to determine the voltage at bus 1. So what we're going to do, assume that this is a PV bus. A PV bus because we know how much is the terminal voltage. Did I specify that here? Not in the slide, but we need to assume that the machine will have a terminal voltage, and that's what you did in the power flow. And we will assume that that is 1 per unit. And the second thing we need to know is how much is the generated power. The mechanical torque in this machine is 0.5 because we don't have losses and the machine is in a steady state. So the speed is 1 per unit. Then the mechanical torque is going to be equal to the electrical power in per unit. So we have 0.5 per unit. So how do we solve that? You took 421. What are the options here? I guess that we have a few options.
You can use V1, V2 over JXL equals P.
You didn't take 421, right?
I took 521.
Very good. So in this system, it's so simple. And because it's so simple, and the system doesn't have losses, so the expression can be obtained immediately. So you said this is B1 over B2 divided by the reactance between these 2 points multiplied by sine of what?
Sine of the angle difference between the two
Points. What is the angle here? Is the angle of the voltage B1, not the angle delta, right? So let's call these B1 is going to be B1 angle theta 1. B2 is B2 angle theta 2. But we know this is the slack bus. B2 is 1 and theta 2 is 0. So basically, this is theta 1 minus theta 2. But theta 2 is 0. That's how we do it. If we don't realize that that's the way to do it, what would be the procedure? A power flow equation, right? And what do you need to do? It's a PV bus. We need to iterate what technique we're going to use. Newton-Raphson. We like Newton-Raphson. Why we like Newton-Raphson? Few iteration, very accurate. Is founded on solid mathematical grounds that we know. We like it. Another technique that might work. Yep, another one. Not that solid. By intuition, we can obtain that equation, recursive equation. That might work too here. What we need to be careful with the implementation of this is that this is a PV bus. Therefore, there is just one unknown. You need to get a complex equation for Gauss, for example, but you just care about the angle, not the magnitude. What about the Newton-Raphson? How many equations do you have? Just one unknown. Very strange Newton-Raphson. That might be a quiz. Solve this using Newton-Raphson. But this equation will suffice in this case. So we solve here for theta 1. Theta 1 will be arc sine of PG XL divided by B1, B2. We put the numbers and we get theta 1. Now we have the power flow solution. This is the, let's call it the power flow solution. And with this, we know exactly how much is the voltage, but also we know how much is the current. How do you determine the current? Well, if you know this voltage, the current is obtained easily. I1 will be V1 minus V2, which is 1, divided by the reactance of the line, also obtained. We know from the power flow then, the terminal voltage and the injected current in that bus. So we know V1, I1. What do we need to do? This is the procedure that I put in the slide. Step 1 is finding the angle delta. So the procedure said This is the angle of the voltage behind the quadrature reactance. So basically, this is going to be the angle of E. And E is the voltage right here behind the quadrature reactance. In this machine, we are ignoring the resistance of the stator. So basically, this is J XQ multiplied by the current I1 obtained from the power flow plus V1. These two obtained from power flow. Okay, so we have initialized the angle delta. Step 2, as we know the current and we know the angle delta, we can solve for this. So that's basically IQ minus JIV. We're going to multiply that equation by exponential of negative J delta. So that is I1 multiplied by negative J delta. You know I1, you know delta. So this is given. We know that. So to calculate IQ, all we have to do is to get the real part of I1 exponential of negative delta. For IV, as you can see here, is negative. That's going to be negative the imaginary part of I1 exponential of negative J delta. So we have the angle, we have the current IQ and IV. What else we're going to do with that circuit? Because we're not done with that circuit. We're going to obtain the voltage in the field winding EFV. There. So we have an expression for this that we already obtained, which is JXQ multiplied by I1 plus B1. We obtained that numerically. We have but by definition, this is going to be equal to the expression we have for the internal voltage, which is going to be XQ minus XD IV plus EFV, all of these multiplied by exponential of J delta. So if we take the absolute value here, we take the absolute value of the exponential, how much is that? 1. So the absolute value of this voltage is nothing else than this. Okay? This was already obtained here. We know that from the numerical evaluation. We calculated E using the solution from the power flow. We know how much is the magnitude. But the magnitude needs to be equal to this. So from there, we obtain that EFV is the magnitude of this internal voltage minus this term right here. And that is step 3. We have that. And then we repeat the step 4. The derivative of EQ prime in time is set to 0. And that is equal to this. We know this. We can determine EQ prime. So EQ prime will be equal to this. And step 5, we do something similar. And EV prime will be equal to that. Step 6, the derivative of the angle need to be equal to 0. So this implies that the speed is 1 per unit. And with this procedure, then we have the initialization of the system. So what is the model that we need to consider here? I will put it right here. So then we have the equation right here. So the first equation is EQ prime dot equal to this. EV prime dot equal to this. Delta dot equal to the classical, the equation we use in the classical model. And then you have omega dot equal to the mechanical torque minus the electrical torque. And the electrical torque is going to be the product of those two terms minus x down. So those are the differential equations. But together with this, we need to consider the algebraic equation. And the algebraic equation is the model that we had before, this plus the algebraic equation that will come from the model that we have for the machine. Now, not in a steady state, but using the model, the dynamic model that we developed before. That one. And this voltage is the voltage that is going to be EQ prime minus EV prime the original model considered another term here that is the difference between the reactances. There. Let me see if I can show that. This is a model, dynamic model we need to use for dynamic simulation. You can see you have this term, xq prime minus xd prime. But in this problem, these two parameters are equal. So this term gets canceled. That's why we obtain that voltage right there. Okay, how are we doing with time? Almost done. So what is the last part missing to do a dynamic simulation? We have the equilibrium point. We assume condition for the power flow. We obtain the voltages, the current injected in the bus 1. With that, we determine the angle delta and all the other variables from the model. Until here, we have all the variables in a steady state. If we simulate that dynamically, that will remain, for all the variables, we will have constant terms. Now, if that system, you have a disturbance, a short circuit, then we need to consider how the variables will change from that point due to the short circuit. And the model we need are these 4 differential equations plus the algebraic equation we obtain from here. So the last part we need here is to obtain what are the equations. So how many equations do we need to obtain in this case? That's the question. All these variables need to be determined here. So you have an equation for EQ prime, an equation for EV prime, an equation for delta, an equation for omega. So all those variables are determined. What do we have? We have missed here EQ and IQ and ID. So from this model, we need to obtain 2 equations that can be added to the model, so those 2 variables are determined. Yeah. What are the 2 equations we get? Kirchhoff voltage law. Complex equation, we separate the real and imaginary part, and we have 2 algebraic equations that can be added to this 4 differential equation, and we solve. Yeah, that's what we're going to do. Be prepared with your laptop. Next class, we will simulate this. Yeah, and if we go fast next Friday, we're going to study the case with 2 machines, how that might change. Okay. Thank you. We're going to be done with this model description, and soon we will start simulating more complex system, and we can pay more attention to the analysis, and that might be very useful for you if you in the future end up doing this type of work. Yeah. Any question?
How did we find, so I know we found the angle for the voltage behind the reactance, but did we ever find the magnitude of the voltage behind the reactance?
We have the magnitude of the voltage in a steady state. For that particular model, we found E phasor completely. You know the magnitude and you know the angle. It's just a circuit.
When did we find the magnitude?
Here. From here, you determine the voltage and the current at bus 1, right? In the model, you know this current, you know this voltage. You know this impedance. So this voltage plus the voltage drop in the impedance will give you E phasor. So that's completely determined. All these steps, you know, you can find this step also when you run dynamic simulation in commercial software. Have you played with PSSE? Some of you. Yeah, when you do that, you need to do that initialization. What the software is doing, all these steps that we're talking. And then when you do the initialization, then you apply the disturbance and see how the system will move in time. The state variables will change in time. Thank you, guys. I will see you on Friday.